I know that title sounds incredibly dramatic, and for that, I sincerely apologize. It's a bit of an overstatement, designed to grab your attention, but the truth behind it is just as mind-blowing. We're not talking about physics literally shattering, but rather encountering something so profound it challenges our understanding and opens up entirely new realms of discovery. Introduction: The Broken Physics, Apology and Clarification. My apologies again for the sensational headline. When we say physics just broke, we don't mean our fundamental laws are suddenly wrong. Instead, it signifies a moment of profound expansion, where new observations push the boundaries of our current theories. It's less about breaking and more about stretching, revealing exciting new frontiers. Today, we're diving into a groundbreaking discovery about gravitational waves that promises to do just that. This isn't just another scientific paper. It's a new chapter in our cosmic story. We're going to clarify exactly what these new waves are, how they were found, and why they're causing such a stir in the scientific community. A quick refresher. What are gravitational waves? Before we get to the new part, let's quickly clarify what gravitational waves are in the first place. Imagine space-time, the fabric of our universe, like a giant trampoline. Heavy objects, like planets and stars, create dips and curves in this fabric. This is what we perceive as gravity. Now, if these massive objects accelerate or collide, they create ripples in this space-time trampoline. These ripples travel outward at the speed of light, carrying energy with them. These are gravitational waves, predicted by Albert Einstein over a century ago in his theory of general relativity. For decades, these waves were purely theoretical, incredibly difficult to detect. They are so faint that even the most cataclysmic events produce ripples smaller than an atom's nucleus by the time they reach us. It took monumental effort and ingenuity to finally confirm their existence. The first detections. A triumph of human ingenuity. In 2015, the LIGO experiment made history by directly detecting gravitational waves for the very first time. This monumental achievement came from the collision of two stellar mass black holes, each about 30 times the mass of our Sun. It was a fleeting, violent event, lasting mere fractions of a second. Since then, LIGO and its sister observatories, Virgo and Kagra, have detected dozens more of these events. We've seen black holes merging, neutron stars colliding, and even black holes swallowing neutron stars. Each detection has provided invaluable insights into the extreme universe. These were high-frequency, short-duration signals, like sharp claps in the cosmic symphony. However, the universe is vast and varied, and scientists suspected there were other types of gravitational waves out there. Waves from even larger, slower events, creating a different kind of cosmic hum. This is where our new discovery comes into play, pushing the boundaries of what we thought possible. The new discovery, a different kind of ripple. So, what's new? For years, scientists have been searching for a different kind of gravitational wave, one with much lower frequencies and incredibly long wavelengths. Imagine the difference between a sharp clap and a deep, sustained rumble. These are often called nanohertz gravitational waves. These aren't from individual sudden collisions like those detected by LIGO. Instead, they are believed to originate from the slow, majestic dance of supermassive black holes. These colossal objects, millions to billions of times the mass of our Sun, reside at the centers of most galaxies. When galaxies merge, their central black holes eventually spiral inward, forming a binary system. As these supermassive black hole binaries orbit each other, they continuously emit gravitational waves. Because of their immense mass and vast separation, these waves have incredibly long periods, sometimes lasting years or even decades. They create a persistent, low-frequency hum throughout the universe, a cosmic background noise that has been incredibly challenging to detect. How do we detect these giant waves? Pulsar timing arrays. Detecting these nanohertz gravitational waves requires a completely different approach than LIGO's laser interferometers. Instead of measuring tiny changes in distance on Earth, scientists use an ingenious method involving pulsars. My apologies if this sounds complex, but I promise to clarify it. Pulsars are rapidly spinning neutron stars, the incredibly dense remnants of collapsed massive stars. They emit beams of radio waves from their magnetic poles, much like a cosmic lighthouse. As they spin, these beams sweep across Earth, and we detect them as incredibly precise, regular pulses. They are nature's most accurate clocks. Scientists monitor an array of these pulsars across our galaxy, forming what's called a pulsar timing array, PTA. Imagine a network of incredibly precise clocks scattered across space. If a gravitational wave passes through our galaxy, it subtly stretches and compresses space-time. This tiny distortion affects the travel time of the radio pulses from these pulsars. The cosmic symphony, measuring tiny delays. Think of it like this. If you're watching a lighthouse from a boat on a wavy ocean, the light might appear to arrive slightly earlier or later, depending on whether a wave is pushing your boat closer or further away. Similarly, gravitational waves cause tiny, measurable delays or advances in the arrival times of pulsar signals. These delays are incredibly small, often just tens to hundreds of nanoseconds over many years of observation. To detect such minute changes, scientists need to observe dozens of pulsars for decades, meticulously tracking their pulse arrival times. They look for a specific pattern of correlations in these timing deviations across the entire array of pulsars. This pattern, known as the Hellings-Downs curve, is the unique fingerprint of a gravitational wave background. Several international collaborations, including Nanograv in North America, the European Pulsar Timing Array, the Parkes Pulsar Timing Array PPTA in Australia, and the Chinese Pulsar Timing Array CPTA have been working on this for years. They've now independently and collectively found compelling evidence for this cosmic hum. Why this is a big deal, the universe's symphony. This detection is monumental because it opens a completely new window into the universe. The gravitational waves detected by LIGO are like hearing individual instruments in an orchestra. A trumpet blast here, a drum beat there. These new nanohertz waves are like hearing the entire orchestra tuning up, a continuous low-frequency hum that permeates everything. These waves are generated by the most massive objects in the universe, supermassive black holes. By studying this gravitational wave background, we can learn about the population of these colossal black holes, how often galaxies merge, and how these mergers drive galaxy evolution. It's a direct probe of the cosmic dance of galaxies. Furthermore, these waves carry information from the very early universe, potentially even from before the first stars and galaxies formed. They could reveal secrets about the universe's infancy, the nature of dark matter and dark energy, and even exotic phenomena like cosmic strings. It's a new way to listen to the universe's deepest secrets. The broken physics explained. What it really means. Let me apologize once more for the provocative title. When we say physics just broke, it's not that Einstein's general relativity is suddenly wrong. In fact, the existence of these waves is a direct prediction of his theory. The breaking comes from the details of what we're observing. Our current models predict a certain strength and spectrum for this gravitational wave background, based on our understanding of galaxy mergers and supermassive black hole evolution. If the observed signal is stronger or weaker than expected, or has a different shape, it could point to new physics. It could mean our models of black hole mergers are incomplete, or that there are other, more exotic sources contributing to the hum. For example, a stronger than expected signal could hint at the existence of cosmic strings, hypothetical defects in spacetime from the early universe. It could also provide clues about the nature of dark matter or dark energy, which we still understand very little about. So, broken means our current understanding might be insufficient, requiring expansion and refinement. What comes next? A new era of discovery. This initial detection is just the beginning. Scientists will now work to refine their measurements, gather more data, and pinpoint the exact characteristics of this gravitational wave background. They will be looking for deviations from general relativity, which could signal the need for new theories of gravity. This is a truly exciting time for astrophysics and cosmology. We are entering a new era of gravitational wave astronomy, where we can listen to the universe in ways never before possible. It's like gaining a new sense, allowing us to perceive phenomena that were previously invisible. My apologies if this sounds overly enthusiastic, but the implications are truly profound. The universe is constantly surprising us, and these new gravitational waves are a testament to that. They remind us that our understanding is always evolving, always expanding. Every new discovery pushes us to ask deeper questions and seek more profound answers. Conclusion: join the cosmic journey. So while physics hasn't literally broken, it has certainly been stretched and expanded in the most thrilling way imaginable. We've opened a new window onto the universe, allowing us to hear the low, majestic hum of supermassive black holes and perhaps even echoes from the dawn of time. This is a journey of discovery that will unfold over decades. Don't miss out on this incredible cosmic adventure. If you found this explanation clarifying and exciting, please consider subscribing to our channel. Hit that like button to help us share these amazing scientific breakthroughs with more people. And tell us in the comments, what do you think these new gravitational waves will reveal about our universe? Your engagement helps us continue to explore and explain the wonders of science.